So our next speaker will be Calvin Beck. And if all goes well, he's going to help us reconcile the infinite memory we want with the few gigabytes we have.
Okay, I'm Calvin, and I'm going to be talking about our approach to memory models for low-level languages like C and LLVM-IR. So LLVM-IR is a common compilation target. It's used by a variety of high-level languages as a common backend in order to target different instruction set architectures. Additionally, LLVM is designed to be an excellent place to perform optimizations, especially as these optimization passes can be shared by a variety of different frontends. Vellum is our semantics and interpreter for LLVM-IR in the Coq proof assistant. The goals are to be able to do proofs about LLVM-IR programs, as well as to be able to verify optimization passes. In order to define the semantics for LLVM, we need to know how memory works. So we need to describe how operations on memory behave, things like reads, writes, allocations, and operations on pointers like pointer arithmetic and cast between pointers and integers. But we also want to define these operations in a way that allows for optimizations. So we notice that LLVM sits in the middle between languages that have infinite memory and assembly languages which explicitly have finite address spaces. Finite memory models are perhaps the most realistic, but they tend to cause problems with optimizations. Adding and removing allocations can be difficult to justify in the finite settings, and it can further complicate alias analysis, as we'll see. Infinite memory models are more abstract and generally allow for a broader range of optimizations. However, existing formal infinite memory models tend to struggle to implement operations which care about the size of pointers, such as pointer to integer casts. We will end up providing a semantics for both infinite and finite LLVM, and we will formally bridge the gap between these two languages. So the idea is that programs will be optimized under the infinite LLVM semantics, which allows for more optimizations. And notably, we will also address an issue with pointer cast to allow for even more optimizations. And after optimizing our program in infinite LLVM, we will safely lower our program to finite LLVM. Finite LLVM is less amenable to optimizations, but it better matches the semantics of assembly languages in the backend. This translation has also been verified to be correct, and also you get a nice transitive property where the final finite program you get is a refinement of your original program in the infinite semantics. So it's hard to convey all of the ways that building a semantics for LLVM's memory is difficult and why existing memory models fall short of our goal in such a short talk. Simply implementing LLVM's memory instructions is not particularly difficult. However, our goal is to verify optimization passes in LLVM. And since optimizations depend upon undefined behavior, our semantics needs to be able to accurately determine when programs contain undefined behavior. This hopefully gives you some understanding of the magnitude of this task. Think about how much subtle and tricky undefined behavior exists in languages like C and LLVM, and now consider how painful it would be to condense all of that into an intuitive and sound Coq specification. That's effectively the position that we find ourselves in, and plotting a course through this minefield is a little tricky. So let's go through a basic example to show the kinds of optimizations we're concerned with, as well as what motivates compilers to introduce undefined behavior in the first place. So to do this, we'll need to consider whether the store to the Q array may alias with P. Stepping through our example, we allocate the P array somewhere in memory. We then store the value 0 at the start of the array. And then we allocate the Q array somewhere else in memory. And then we store 3 to a specific index in the Q array. But where does this value actually get stored? It could be within bounds of Q. It could overlap with P of 0. It could go somewhere else. We don't know. And in order to know, we would need to know where P and Q are allocated and what the value of f of 0 is. This can be difficult or impossible for a compiler to keep track of. F of 0 could be a complex expression or an external call that the compiler could not determine the result of. Programmers and compilers will reason about, in exactly the same way to justify this optimization, though. They will simply assume that the store is in bounds and therefore cannot overwrite P. If that's the case, we can perform store forwarding and eventually dead code elimination to get the optimized program on the right. Programs that invalidate this assumption have undefined behavior, and optimizations may not be correct on programs with undefined behavior. This is what makes optimization is tricky in low-level languages, direct memory access provides many situations for aliasing to arise, which block optimizations. Compilers aren't smart enough to detect things like out-of-bounds accesses, and instead have to just assume that they don't happen. The next conundrum that we'll explore is finite memory. It's tempting to make LLVM a finite memory language, as it matches the assembly languages that it targets. Unfortunately, finite memory is disastrous for optimizations, which change the amount of memory being allocated. We'd like these two programs to be equivalent, but in a finite setting, they're not. The program on the left may run out of memory and never end up printing anything, and removing the allocation would allow the program to print instead of running out of memory. But this introduces a new behavior to the program, meaning that the optimization would not be valid. All of this gets in the way of important program transformations, and this can be problematic for register allocation and spilling, which are important. So finite memory is problematic for optimizations in at least one way, but the problems go even deeper. Finite memory introduces side channels for creating aliases, which again block optimizations like store forwarding. Let's consider, for example, a 2-byte memory where we allocate 2 bytes separately. No matter where we allocate the first byte, we know that the second allocation has to be in the other location in memory. This allows us to construct an alias to the second allocation, even though we have never directly observed its location. This might seem like an artificial problem, and you might be thinking, who cares about this crazy cursed program? But the issue is, if you want to prove an optimization correct, you have to consider all programs and only trigger the optimization when it's valid. Detecting these side channels is difficult, making it hard for a compiler to rule out aliasing. There are tricks to get around this problem, like the twin allocation memory model, which uses a clever trick with extra allocations and non-determinism in order to detect this and trigger undefined behavior. But this is pretty sophisticated and has some limitations, and we wanted to have a simpler solution. So notably, infinite memory models don't suffer from this problem because we have an unlimited number of locations that we can allocate from. So this is where we get to our two-phase memory model. Finite memory is hard and causes tricky problems for a lot of optimizations. So instead, we decided to just pretend that we have unlimited memory. We can do all of our optimizations in the well-behaved infinite memory world, and then safely convert our infinite programs to finite ones with the same behavior modulo the possibility that they run out of memory. We model our primitive memory operations via this memspec monad. The memspec monad maps initial memory configurations to a set of possible results. This may indicate that the operation raises undefined behavior, runs out of memory, or that the operation can run successfully, yielding the resulting possibly unchanged state of memory, as well as the result of the operation with the appropriate type. The specification of operations will be shared between both the infinite and finite stages, but the size of the memory component of memspec will differ between the two. The operations that we'll model are just the operations we mentioned before: reads, writes, stack allocations, heap allocations, and free. So let's take a quick peek at how these specifications work for malloc. We'll allocate 2 bytes on the heap. In the infinite memory model, we will get a set containing every possible way we could allocate these bytes in the current memory. Our semantics is non-deterministic, allowing us to detect address guessing and model things like pointer comparisons appropriately. With infinite memory, this is an unbounded set, and as there are unlimited locations to allocate from. The malloc specification in a finite model, in this case a 3-byte memory model, will look similar, but notably there will only be a finite number of possible ways to allocate these 2 bytes. We've set up a refinement relation between the infinite and finite operations. It ensures that the finite memories on the right-hand side can be lifted to infinite memories on the left-hand side. This guarantees that finite operations can effectively simulate the infinite ones. And of course, we've verified this relation for every operation in our memory model in Coq. This refinement relation also takes into account undefined behavior and out-of-memory events. So we always allow out of memory on the right-hand side, which allows finite programs to run out of memory instead of continuing to execute. And if undefined behavior is on the left-hand side, we allow any behavior on the right-hand side, allowing us to perform optimizations without worrying about ill-defined programs. As previously noted, we've integrated this two-phase memory model into Vellum to stress test it under a large and realistic semantics. This has highlighted a number of tricky situations around things like casts, undef values, structured data types, and just issues with how big LLVM is as a language. So one tricky issue is pointer to integer casts. In an infinite memory model, pointers are unbounded, so casting them to finite integers can result in truncation. This means that the casted p2 in this example may alias with an unexpected location in memory instead of pointing to the same place as p. And again, unexpected aliasing can block optimizations like store forwarding. And so how do we deal with this? The solution is actually quite simple. We just need an integer type with the same cardinality as pointers, which we will call the endpointer type. Such a type even exists in C already, but we'll have to add such a type to LLVM. In the infinite model, int pointers will be big ints, and in the finite model, they can, for instance, be bounded 64-bit integers if we have a 64-bit address space. This allows us to patch up the issues with casts, easing aliasing concerns and allowing us to perform optimizations even in the presence of these casts. Because the implementation of int pointer differs between infinite and finite models, we have to be careful when translating infinite programs to finite programs. In the infinite world, this program counts up indefinitely, but if the finite int pointer value is allowed to overflow, the loop would terminate and instead allowing the program to do evil new behaviors. So a correct translation of this program to the finite world will need to add bounds checks on the int pointer arithmetic. There are more details in the paper, but we believe that this will have a minimal impact on performance, as these checks can be eliminated in most of the cases where pointer to integer casts are used in real programs. So we've previously defined a refinement relation on memory operations, and eventually we'll need a refinement relation on full LLVM programs. And to do that, we essentially just lift the refinement relation on memory operations to the level of the languages themselves. Our semantics is non-deterministic, so we end up with a tree of possible traces our program can have. This shows the semantics of this program under the infinite memory model. It prints start, and then it prints the address allocated. There are an unbounded number of possible values that could be printed. And finally, the program prints end and exits. In the finite semantics, the behavior of the program is identical, except it may give up early, claiming that it ran out of memory, and there are not as many possibilities for addresses returned by malloc. We have also proven that the finite version of the language agrees with the infinite version up to this refinement relation. For some more intuition about the infinite to finite refinement relations, we can consider kind of a set-based semantics. Each of these letters represents a different behavior, which is just one of the traces down those trees of executions from before. We can perform optimizations on infinite programs, refining their behavior to subsets of the original set of behaviors. And then we can translate the optimized program to a finite one, which again gives you a subset of the original set of behaviors with the possibility of the program running out of memory. Finally, we can see the transitive property that we get. The final set of behaviors of the finite program after all of these steps will be a refinement of the original set of behaviors as well. Note that if we translate to a finite program before performing optimizations, we might not end up at the same place. For instance, a program may run out of memory immediately if translated to the finite world right away, but we could perform optimizations to remove allocations in the infinite world, which could allow the finite program to make more progress. There's a lot more details in the paper about all of the particularly handling of the LLVM language itself. There's a lot of information on how we've integrated better handling for UB in Vellum, support for undef values, details on the verified executable implementation that allows us to do testing and run LLVM programs, as well as a deeper comparison to related work and more details about the COC development. So in conclusion, we have implemented infinite and finite memory models and integrated these into an LLVM semantics. We have verified the connection between these infinite and finite languages as well. We are also able to verify program transformations and optimization passes, and our infinite memory model can support optimizations in the presence of pointer to integer casts. Finally, artifacts are available, and you can find our work on GitHub. Thank you. Are there any questions?
Hey, Stephen Dillon, Chen Street. I'm curious how much trouble the tricky pointer provenance rules of C and C++ cause for this. There are examples where there are pointers which are distinct in a memory model but compare equal bit for bit. Do you did you have to deal with any of this stuff in your infinite model?
Sorry, the question is about pointer provenance?
Yeah.
Yeah, so we have provenance associated with our pointers, which does potentially cause issues when you translate to integers. It's kind of an orthogonal question of whether you transfer provenance to integers and back.
Yeah.
Currently, when you cast a pointer to an integer and back, you get a wildcard provenance in our model.
Yeah. Okay. Okay. Thanks.
A practical question: with what version of LLVM you verified this, and how you will sync with the future LLVM updates and versions?
So we haven't quite nailed down which version of LLVM we support. I think the version that we test against is like Clang 13 or something. Vellum is currently like a large subset of LLVM, but not like all of LLVM. So yeah.
Thank you.
Okay, then let's thank the speaker again.